Hello and welcome to today's revision session where we're going to look at momentum in the forces topic for GCSE Physics. So in today's revision session we're going to cover three key areas. We're going to look at what momentum is, we're going to look at the conservation of momentum, and we're going to look at the change in momentum. So the first idea we're going to look at is momentum. Now, momentum is how difficult it is for an object to change its motion. So if it's difficult for an object to change its motion, it has a high momentum. If it's easy for an object to change its motion, it has a low momentum. So for example, a rugby player has a high momentum. Why is this? A moving bus or a truck has a high momentum. Why is this? Because they have a high mass and they've got a high velocity, which gives them a high momentum. Now, the momentum of an object is dependent on two factors of the object, the mass of the object and the velocity of the object. So we can express this in the form of an equation. Momentum equals mass times by velocity. Now you're expected to recall and memorize this equation for your examinations. And we can symbolize this with the symbols P equals mv. Now momentum is given the symbol P as the first letter of the Latin translation of momentum or impetus begins with P. Now, basically, Isaac Newton realized that a resultant force was needed to change the velocity of an object, but Newton also realized that the effect of the resultant force was dependent on the object's mass. Now, we know this in the modern day as F equals ma, Newton's second law of motion. So what Newton did is he decided to simplify the system, and he considered the product of the mass of an object and the velocity, the momentum. Now, we can use this to determine the units of momentum. Now, we can work out the units of any value by looking at its equation. Now, we know momentum is mass times by velocity. Mass is given in kilograms. Velocity is meters per second. And when you multiply values, you basically push the units together. So the units of momentum are kilogram meters per second. So we've combined the units because there's a multiplication going on. So we can also express it in the following version or that way as well. Now, an object, it has to have momentum if it is moving. If an object is not moving, it has no momentum. Momentum is a dynamic quantity. Think about why this is. Because if the velocity is zero, the momentum is zero. Because when you times any number by zero, you get a zero value out. Now, momentum is also a vector quantity. And the direction of momentum is shown by the sign of the calculated value, plus and minus. So objects moving in opposite directions have opposite signs. So this means momentum can be changed by either altering the speed of the object or the direction of the object. So unless stated in the question, you can assign the plus and the minus with a particular direction. So what do we know so far? Newton defined momentum to be mass times velocity. The unit of momentum is kilogram meters per second, and momentum is given the symbol of P. And a momentum is a dynamic quantity. Any object moving has to have momentum. So momentum is calculated with the equation momentum in kilogram meters per second is equal to mass in kilograms times by velocity in meters per second. Momentum has both a magnitude and a direction. Momentum is a vector. And if objects are moving in opposite directions, they have opposite momentums, which is signified by one value being a plus and the other value being a negative. Now, this allowed Newton to write his laws of motion in terms of momentum. Newton's first law: objects will stay at rest or move with a constant velocity unless acted upon by a resultant force, becomes a resultant force, changes the momentum of an object. Newton's second law, which is F equals ma, becomes the resultant force is proportional to the change in momentum every second. And Newton's third law, that when two objects interact, they exert equal and opposite forces of the same type of each other, becomes that for a system of objects, the total momentum of the system before equals the total momentum of the system after, as long as there's no external forces on the system. Which leads us into the conservation of momentum, which is the next part of this topic. So, in collisions or explosions, the total momentum is conserved. This means the total momentum of the system before is the same as the total momentum of the system after. So, in this example, the momentum of object 1 plus the momentum of object 2 before must equal the momentum of object 1 plus the momentum of object 2 after the event, after the collision. Now, individual objects can change their momentum in a system, but the overall momentum of a system must stay constant. So, for example, before the collision, object 1 might have a momentum of 2 kg meters per second, and object 2 might have a momentum of 0 kg meters per second, so the total is 2 kg meters per second, but after the collision, they both have 1 kg meter per second as the momentum, so the total is 2. Now, what this tells us is object 1 and object 2 have each changed their momentum, but the total overall is conserved. 2 equals 2. Now, as we can see before, we can actually expand this out. So we can say that mass times velocity equals mass times velocity, because momentum is mass times velocity. Now, in an examination question, you'll be given all the values except one of mass times velocity equals mass times velocity and asked to work out the missing value. So one of the most common laws of physics is the conservation of momentum, which is based on Newton's third law of motion. In any collision or explosion, if no external force is applied on it, the total momentum of the entire system is the same before as it is after the collision. So mass times velocity before equals mass times by velocity afterwards. So this can be the case for a collision. So momentum before equals momentum after, and there's no external forces acting on the system, or the system is a closed system. So momentum of A plus momentum of B equals momentum AB in this particular example. Now we can consider any system which has at least one dynamic object before contact a collision. So an example question would be the following. Here we have two balls. Okay, they are in the situation together, they collide with each other and they move off after the collision. So what's the velocity of the two balls stuck together after the collision? Well, step one, work out the side of the equation you can do. Can you do the before side or can you do the after side? Well, you can do the before side because you've got the mass and the velocity of all the objects before the collision. So you work out the total momentum before by doing mass times velocity of each one. So 2 times by 5 plus 4 times by 0, so 10 plus 0 equals 10 kg meters per second. Now step 2, you say momentum before equals momentum after. So if the momentum before was 10 kg meters per second, the momentum after is 10 kg meters per second. Then step 3, use the equation momentum equals mass times velocity to work out either m or v depending on what the question is asking for. Now the question is asking for v, so v equals momentum over mass 10 over 6. We know the mass is 10 because the mass of 4 and 2 have now stuck together, so we get an answer of 1.7 meters per second. Now you then carry out a logic check. Does your answer look sensible? Well, think about it. The mass of the moving object has increased after the collision, so therefore its velocity should go down because it's more massive. So therefore, has it gone down? Well, it's gone from 5 to 1.7, so yes, it has. Now, the mass moving afterwards is larger, so the object will be moving slower than before the collision. Now, another event where momentum is conserved is an explosion. Now, the total momentum of a system in an explosion is 0 because beforehand the object is not moving. It has a total momentum of 0. But after the explosion, both objects have a non-zero momentum. The two objects are produced as fragments of the original object. So overall, though, the momentum of the system must be 0 to conserve momentum. So how do we have this? Well, you've got to consider the direction because the fragments are going in opposite directions. This means that one has a positive momentum and the other has a negative momentum. So when you add the two objects and one is a plus and one is a minus, they'll add together to give 0 to conserve momentum. So for example, plus 20 kg meters per second and minus 20 kg meters per second equals 0 kg meters per second. So how can you work out an answer in an explosion? So in an explosion, two objects A and B explode when they start at rest and momentum is conserved. So we know that the momentum before is 0, step 1. So step 2, momentum after must be 0. So 0 equals momentum of A plus momentum of B. So therefore momentum of A equals minus momentum of B. This makes sense because A and B move in opposite directions, so you can work out a value that you require. So for example, what's the velocity of bomb fragment 1 in this particular situation? Well, what do? You remember that the total momentum afterwards must equal the total momentum before, and if it's 0 before, because 10 times by 0 equals 0, it must be 0 afterwards. So what you then say is, to get to be 0, fragment 2 must equal fragment 1, where fragment 1 is a negative because fragment 2 is a positive. So what you do is you work out the fragment you know about, and we know about fragment 2. So we say 7 times by 2 equals 14 kilogram meters per second. So therefore, fragment 1 must be minus 14 kilogram meters per second. And we then use our step 3, which is we use the momentum equation to work out either m or v, and we want v in this case. So v is momentum over mass. It's minus 14 over 3, and it's minus 4.7 meters per second. Minus meaning it's moving in the opposite direction. Now, logic check. The heavier fragment should be moving slower to have equal and opposite momentums, and that's the case. The lighter fragment is moving faster. Now, we see the conservation of momentum in many different examples, such as firing a gun. Okay, because when you fire a gun, you'll notice a recoil, and that's an example of the conservation of momentum. So how does this link to the concept of momentum? Well, let's consider a gun and a bullet before it is fired. So before it explodes, it's not moving, so the total momentum must be 0. So therefore, after the object is fired, if the bullet has a positive momentum, the gun must have a negative momentum to cancel out that positive momentum of the bullet to get the total momentum to be 0. So the total momentum after will be 0. So this means there's movement in opposite directions. Now let's think about this. The bullet has a lower mass than the gun, so for mass times velocity equal mass times velocity, if it's got a lower mass than the gun, it must have a higher velocity. So the gun must have a lower velocity than the bullet to have the same magnitude of momentum, because the objects need the same magnitude of momentum to cancel out and give 0, because the plus and minus number must be the same. So the momentum of the gun equals the momentum of the bullet, and therefore mass times by velocity of the bullet equals mass times velocity of the gun. So when we work it through like that, for both values to be the same, we need to have 1 as a plus and 1 as a minus, so they equal each other out. And in the collision or explosion, the larger the mass, the lower the velocity. We observe this effect in all guns. Now the final topic we're going to look at is a change in momentum. Because, like we said before, that whilst the total momentum in the system before and after a collision or explosion is the same, the individual momentum of objects can change. So to transfer momentum between objects in a system, there must be a resultant force acting on a system. Now, the larger the resultant force on the object, and therefore the higher the acceleration or deceleration, the faster the change in momentum of the object. Now, the faster the change in momentum, which is sometimes called impulse, between objects, the greater the resultant force. Now, in a collision, a large resultant force or impact force is bad for you because it can lead to bones being broken or worse. So it's the aim of any crash or any explosion to reduce the resultant force to a minimum. And we do this by ensuring that change in momentum happens as slow as possible. Because if the momentum changes for an object, we call the change in momentum the impulse. And in a collision or explosion, the longer the impact time for impulse, the less the impact force is exerted. And our equation to show this is that force equals change in momentum divided by time taken. So force in newtons is equal to change in momentum in kilogram meters per second divided by time taken in seconds. Now this equation is actually given to you in your exam. You don't need to memorize it, you just need to use it. Now we remember that momentum is mass times velocity, so we can say that change in momentum is change in mass times velocity over time. However, we'll also know that mass doesn't really change in a collision, so it's velocity that changes. Okay, so it's actually mass times by change in velocity over time taken. Now, the longer it takes for an object to stop in a collision, and therefore for its momentum to change, the less force is required to stop it. So when the impact time is large, the resultant force is small. So for speed and car crashes, then the time of the crash is very small, so the impact force is huge, which can lead to be a very dangerous situation. Now the rate of change of momentum for for an object is directly proportional to the impact force exerted on it. So this is why cars have crumple zones at the front and the back. They're weak enough to crumple but strong enough to do so slowly. This increases the time to change momentum, so decreases the resultant force on the car. Car passengers have similar protection. Airbags, seatbelts help increase the time it takes for passengers to stop, so as the time to change momentum increases, the resultant force decreases. So we can see it in such like this. So the force that is produced in the collision which changes the momentum of the object is called the impact force. So whilst the total momentum of the system stays constant, the momentum of one object can change. Now this is very important because as the change in momentum is the same regardless of the time of collision, the aim of all collisions involving humans is to have a low impact force which decreases the chance of injury, and this is done by increasing the contact time. Increasing the contact time decreases the impact force experienced by the object, whilst decreasing the contact time increases the impact force experienced by the objects. Crumple zone, pattern, helmets, sidebars, crash mats, seatbelts, all safety features work by increasing the impact time for a collision, so the impact force experienced by an object is reduced. And this is illustrated if you run into a brick wall. Because the brick wall is very rigid, the time of collision is very low for the change of momentum, for the impulse to occur, so it means the impact force is very high, which is why it's likely you'll break your nose if you run into a brick wall. However, a sponge wall, a sponge pad, is very flexible. It will give. So the time of collision is very high for the impulse to occur, so the impact force is low, which is why you don't hurt yourself if you run into a sponge wall or to a crash mat. Now just remember that in our collision, in our explosion, when two objects interact, they exert equal but opposite forces on each other at the same time. So the change of momentum of one object is equal and opposite to the change of momentum of the other object. So if one object increases momentum by plus 20, the other will decrease by minus 20, and this allows the total momentum of the objects before and after the collision to be the same, conserving momentum. So let's summarize what we've learned. Momentum is defined by the equation momentum equals mass times velocity, where momentum is in kilogram meters per second. In a closed system, the total momentum before an event is equal to the total momentum after an event, and this is called the conservation of momentum. When a force acts on an object that is moving or able to move, a change in momentum occurs, which gives us the equation F equals m delta v, where m delta v is change in momentum, over time, i.e. force equals the rate of change of momentum. And you should be able to explain how safety features like airbags, seatbelts, gym mats, cycle helmets and cushion surfaces for playground work with reference to rate of change of momentum. So I hope you've enjoyed this revision session looking at momentum, conservation of momentum and change of momentum. I hope you found this very useful and have a lovely day.